It's now a fact that gallium nitride technology become crucial for power electronics industry for power electronics applications. And that we can see that how the market share is growing year by year for my gallium nitride technology. It is not now limited to consumer electronics. It's now also increasing to automotive sector, also space industry, LiDAR application, and therefore in near future, we expect even the market share will increase for this technology, and it will also increase up to the power supply applications, UPS, etc. So let's see why this gallium nitride technology. Um, I will hide this. Okay. So yeah, let's see that why this gallium nitride technology gaining more popularity day by day. So the alternative we have today, the silicon MOSFET, silicon carbide, and the superjunction MOSFET, if we compare that with the gallium nitride technology, we can see that the gallium nitride devices have the ability to operate in high breakdown voltage and with low on resistance compared to the other technologies available. And this high breakdown voltage can with this high breakdown voltage ability, it's possible to make the circuit in high voltage, high current with higher efficiency. Why? Because a low on resistance will help to have lower conduction loss. Because of it's a high electron mobility device, it also gives high switching speed. And the high switching speed helps to operate a circuit in higher switching frequency, and that helps to reduce the passive component size in the circuit. Therefore, it enables to a compact, cost-effective, lighter weight device. However, these GaN devices till today dominate in the market is either as an off-the-shelf components or the discrete components. But this extremely good frequency capability of gallium nitride device also introduces some challenge to operate this efficiently. So often we see in the GaN-HEMT device creates a high gate ringing during the switching transitions, and that gate ringing also reflects to the output of the circuit. And the high ringing also creates the not only creates a switching performance problem, also sometimes impacts the gate reliability. Now, why this high ringing causes? During the turn on of the GaN-HEMT device, the parasitic inductance, gate resistance, and the input capacitance creates a LRC charging path. And due to this LRC charging path, there is a volt oscillation we see in the gate voltage. Now, higher the loop is, the bigger the oscillations we see, and that creates the gate ringing during the switching transition. And while the switch is turning off, it creates high DVDT. And due to the high DVDT, this quickly charges the input capacitance, and that rises the gate voltage during the switching off. Sometimes this gate voltage spike is so high that it can even go beyond the threshold voltage. So it means you will see the false turn on during the switching off transitions. And we don't want it. So therefore, one way is to reduce this gate loop inductance as much as possible to have the less ringing. And by doing this, we can to reducing the gate loop inductance, we can bring this gate driver as close to the as power device as possible. And that calls for a monolithic integration. Besides that, we know that discrete gallium nitride gives a higher switching speed comparative to the silicon alternative, And we have also seen that GaN IC, so the monolithic integration is even enables the higher switching speed compared to the discrete GaN. So therefore, this higher switching speed makes possible to integrate higher power and also to have the more robustness in the circuit by reducing the gate overshoot and undershoot. So this also increases, as I said before, that the higher switching speed also helps to reduce the filter size, the passive component size. So GaN IC is actually could be an alternative which can really follow the power electronics trend to make a faster, smaller, lighter, and cheaper circuit and system design. Therefore, we are convinced that to unlock the full potential of fast switching gallium nitride technology, monolithic integration is essential. Uh, and here in today's talk, therefore, I will talk about the GaN IC technology. And to have that possible, that monolithic integration, what are the challenges we have faced? And then I will also show you some GaN IC demonstrations, what we have developed already. To evaluate the performance of GaN IC demonstrator, we have also implemented them in the prototype level. So I will also give you an overview of some prototype level implementations and the measurement results of that. And at the end, I will give you a brief of our offerings through this ASCENT Plus project. Thanks to this ASCENT Plus project, you can also access some of our GaN IC test samples by using this project platform. I will show you how to do this and what are the samples are available to access to the showroom. So let's start with the challenges of monolithic integration. What do I mean by GaN ICs? So let's say that we wanted to build a half bridge switch. And in case of a half bridge switch, we know that one high side switch is connected to a low side switch, and that is makes a half bridge switch, which is one of the most essential components in any kind of synchronous power conversion. So if I have one high side switch, one low side switch, and then both of the discrete switches are driving with an external driver, then we have a 3-die solution. To have a monolithic integration, we first tried to have a two-die solution to have one hybrid switch, one switch with an integrated driver. So two of such IC, like one IC contains one switch and its driver, two of such ICs are connected to have a half-bridge switch. Or we also have one half-bridge switch in a single IC. So it means in an IC, we have one high side switch and one low side switch connected in series and form a half-bridge switch. And then you can drive that half-bridge switch through an external driver. So this is also a 2-die solution. Then we went further to have a single die solution where we have integrated high side switch, low side switch, and their driver, everything in a single IC. So starting from a discrete components, we have now a single die where hybrid switch and their driver, and we have further also integrated several functionalities like the date time controller, comparator, and level shifter, etc. So to achieve such monolithic integration, we have faced some challenges. There are some technological problems as well as circuit design problems. I will first start with the technological problems, where we have seen that even to have a monolithic integration in half bridge, there were some effects we have first faced, and also we needed to solve the low voltage device problems, because we know for any kind of driver circuits we need the logic gates, the analog blocks, etc. And the suitable passive components were also needed to integrate in terms of have a good performance. And then in the next section I will show the circuit design problems what we have achieved. So Let's start with the CMOS technology. We know in a CMOS technology, we have a body effect. Now, what is a body effect? If there is a potential difference between the source and the substrate of NMOS, let's say, that if there is a potential difference between the source and substrate, we see the threshold voltage changes. That also we see in the equations, that the threshold voltage of a NMOS has an influence of the substrate to bulk potential. Now, ideally, the threshold voltage can only be operated by a gate voltage, but we have seen the influence of substrate to source potential. That is sometimes called a backgate, and that is what this effect is also known as a backgating effect. So therefore, if there is so here you can see a cross section of an NMOS. So if there is a difference between a P well and the potential of source, then there we can see there a body effect. Now, how we see the same thing in P.GAN HEMT. Here I'm showing you a cross section of P.GAN HEMT, where you can see a gate with gate metal surrounded here, a source with the source metal stack and the source metal fill plate going through the gate metal, and a silicon substrate. So we see the backgating effect here in the silicon substrate. How? If the potential of this substrate is different than the potential of source, then we see a similar effect as we see in the NMOS, the threshold voltage change. And this problem became eminent when we are trying to do a monolithic integration for half bridge. So if we have a discrete device, like a discrete high side switch and a discrete low side switch, then in both of the cases, the source and the substrate are connected in a same potential, and we do not see a backgating effect. But when we do a monolithic integration, so it means we have high side switch and low side switch are on a single silicon substrate. Then we see the backgating effect, because we can only connect the substrate with the one source. So let's say if the so in this case, let's say for the low side switch, the source is connected to the substrate through the backside of the high side switch. And in this case, let's say we connect the substrate to ground. And the high side switch is connected to VDD, and the source of low side switch is connected to ground. It means the substrate contact is also connected to ground. Let's say a situation where the low side switch is off and the high side switch is on, and we have connected the VDD as 200 volt. Then the low side switch is now 0 volt, the source of low side switch, and the substrate is also at 0 volt. And because the high side switch is on, so therefore this node is contents kind of the same as VDD. So let's say a little bit of drop because of the RDS on. So we can actually see in this node, it has around 199 volt. Now my substrate contact is actually in 0 volt. So in this case, we will definitely see current in substrate. And if we do not connect the substrate actually through the source, if we keep the substrate floating, then definitely the substrate and the source of high side has a kind of 199 volt gap. So the substrate and the bulk potential is not same, and we will see a backgating effect, and that affects the performance of high side switch. So how did we solve it? We have connected high side and the low side switch on an SOI substrate instead of a silicon substrate. In the SOI substrate, we have used the buried oxide and deep trench isolation to have low side switch and high side switch galvanically isolated. By doing this, you can see substrate of the low side switch And also substrate of the high side switch is source of the high side switch is connected through the silicon substrate, the top layer of the SOI substrate, the thin silicon layer separately. And in that way, the substrate source potential for both of the switches are zero. And that way we can reduce the backgating effect. Actually, we can eliminate the backgating effect. Um, so here I wanted to show you what happened if we do it instead of a SOI on silicon substrate. So in this case, we have the hybrid switches on GaN on silicon, and the substrate of the silicon is connected to 0 volt, which is connected to the low side of the source. Then we see that when we go in the higher voltage like 100 volt and 200 volt, the normalized drain current is reduced. But in case of GaN-on-SOI, so this is a cross section of GaN-on-SOI half-bridge switch, we see that the backgating effect is completely eliminated and normalized current reduction is also eliminated even with the higher voltage. Now you can say that we can do this thing that we do not connect this silicon substrate to any potential, so you can keep it floating. We have also tried that, but that did not solve the problem. We see, despite the fact that where silicon is floating here, the silicon substrate, we still see the backgating effect because although it is not connected to any particular potential, it will charge to a random potential, and then that creates the backgating effect. Therefore, with this deep trench isolation and the half-bridge switch on the SOI substrate, we see the backgating effect is completely eliminated. Uh, so after that, we need the logic devices, because we know for any kind of analog block in the driver stage protection circuit everywhere, we need logic devices. So for us, the logic devices actually is the layout scaled version of a power P.GAN HEMT by doing shorter gate width and the shorter gate to drain distance. We have tested the gate width up to 2 micrometer. Here you can see the variations of the gate width between 2 micrometer to 6 micrometer, where you can see the threshold voltage change is unaffected. Another problem is here in gallium nitride technology, we do not have a complementary device like for a CMOS. So for CMOS, we have a NMOS and a PMOS. But in this case, we have enhancement type HEMT, which you can think like a NMOS. So a N-type HEMT. We do not have a P-type HEMT device. Therefore, to achieve inverting function, we use that with an RTL logic, register transistor logic. And we have used the 2DAG register as a load register. Also, some passive components that's included in our PDK, high ohmic register, and that is made with the 2DAG registers, that's 600 ohm per square. Low ohmic registers also we have developed some using the ohmic metal layer of the ohmic contacts, that's 1.7 ohm per square, and some integrated MIM capacitor, that's 0.3 femtofarad per micrometer square. As I said, that no complementary device in this technology, therefore we had to use RTL design instead of DCFL design to have the inverting functions, and that basically makes a trade-off between the switching speed and power dissipation to design the register in the RTL logic. That also creates definitely the difficulties in the driver design and the logic gates and the analog subcircuits in order to have a particular gain and power dissipation, power loss. There is I will show you some proof of concept demonstrator here. As I was saying, the inverter. Here you can see N-type FET is connected in series with a 2DAG register to have a RTL logic. And this resistance value, if we increase this will definitely increase the gain of the circuit. But that will come with a penalty of power dissipations and the lower switching speed. So therefore, this resistance need to be optimized properly to have a balance between the gain and the power dissipation and the switching speed. So we have the inverter, NOR gate, NAND gate, and the flip-flop here. And you can see from the measurement result that the functionality are achieved. This is the picture of the device layout after fabrication. Here, I'm showing you an analog block of a comparator. So from the measurement result, you can see that here the VDD is changing from 3 volt to 7 volt, and the reference voltage we have set here as 4.5 volt as comparator works. So when the reference voltage is changing, then we can see in the output that the voltage flips, and that is a thing that's a functionality of the comparator. Uh, it's a UVLO circuit we have realized through GaN-IC. UVLO is an essential part of a driver component. So it's under voltage lockout. It makes sure that when a voltage is lower than a certain voltage, then it's turn off the circuit. So again, in the result, you can see that we have that functionality in this. We have implemented that through, again, an RTL logic. Here we put the VDD at 8 volt and the reference as 4 volt. The VACS node follows the VDD. Therefore, when the VDD is 8 volt, the VACS node is higher than the reference voltage of 4 volt. And that makes the VC low. So this node is low, and therefore H1 transistor is turned off. When we reduce the VDD from 0 volt slowly, this node VCS is also following VDD, and therefore it's also start reducing. And when this voltage become lower than 4 volt, then VC goes from low to high. And that time when VC goes from low to high, it turn on the H1 transistor, and therefore it turn off the entire circuit. We can again restart that by increasing the VDD after a certain voltage. This is a picture after fabrication of a UVLO circuit. Next slide. Okay, I'm sorry, I am not able to access my slides. I will just stop sharing for a moment. And okay. I will share my screen again. Sorry for the inconvenience. So can any of you please confirm that you can see my screen?
Yeah, we can see fine, Urmimala.
Okay, thank you. Okay, so here one integrated driver with a low side HEMT where we have used a push-pull driver and an RTL behind that before that. We have tested it up to 20 megahertz, where you can see that up to 10 megahertz it gives a smooth and clean signal. And in 20 megahertz, although we see some distortion, but we can still see the switching characteristics. These are a result of the double pulse test to show the switching behavior. And then here is a layout of 200 volt half bridge switch with integrated driver. So the high side and the low side switch and the driver stage here. Here the level shifter is also integrated. This result shows the switching frequency up to 1 megahertz with the rise time, and the fall time is like 25 and 38 nanosecond. This is the one is packaged in DIL, dual inline package. We have implemented this hub bridge with integrated driver in a 48 to 1 volt buck converter. This is the switching transitions of the buck converter, where we have operated the converter at half a megahertz, and from this measurement result, you can see that we are able to achieve a step down directly from 48 to 1 volt by using this GaN IC. So apart from the under voltage lockout circuit, we have different blocks like over temperature protection, over current protection, etc. And then I will show you some prototype level implementation to evaluate the performance of our GaN IC. So here we have made a boost converter and a 3 prototype of boost converter. 3 are of the same converter with the same parameters and same design. Only one PCB has a imec half bridge switch with integrated driver, and other 2 has imec half bridge switch, but that is driving with an external driver. In one case, we are using a TI LMG 1210 driver, and in the another case, we are using a Silicon Labs driver, but in both of the cases, we are using the imec half bridge switches. And these switches are packaged in a HSO P24 package, where the backside is connected with a metal, and that can be directly connected to the thermal vias, which will be used as a heat sink and help to do the good heat transfer. So the boost converter is designed by considering the parasitics and in the parameter where it can operate up to 50 volt input voltage and 100 volt maximum output voltage. The input power is limited to 200 watt, and although we have operated a nominal half a megahertz, it can work up to 2 megahertz. And the ripple maximum input ripple is designed as 15% and output as 5%. So here I will show you the switching transitions, where I'm comparing between the 3 of the PCBs. So that means the integrated driver with the external drivers of hub switches. All the 15 nanosecond half a megahertz with 25 volt 1 ampere input. So here we can see that when the low side switch turn on and the high side switch is turning off, the switching transition in this case, the turn on time is 30 nanosecond for the integrated driver, and 37 nanosecond and 40 nanosecond in both of the cases where we are using the external driver. And the another switching transition where the high side switch turning on and the low side switch is turning off. In that case, also we see the fastest transitions is from the integrated driver, that is 10 nanosecond. That's followed by 12 nanosecond and 26 nanosecond for the other two drivers. So as expected, for integration, the loop inductance is reduced, and therefore we can achieve the fastest set switching with less ringing. That was the main reason to do this test, to see that whatever with the target of the integration, if that is verified through the measurement result, and we have seen that is indeed the case. We have also changed the input current and the input voltage in different level to check that what happens, and we see in all the cases the integrated driver shows the fastest transitions. So here I'm finishing my talk. In the last phase, I will tell you that this 200 volt E-mode GaN power HEMT discrete device, 200 volt half bridge switch, a low side HEMT with integrated driver, and a half bridge switch with integrated driver. You can access these test samples through ASCENT Plus project. You can go to the ASCENT Plus network, and there you can go to this link to check how you can access these test samples, and you can Through the inquiry form, you can have these test samples for free. Besides that, also this is part of the ASCENT Plus offering. You can also access to our MPW service, where you can have your customized prototyping and design for 200-fold platform. Again, from the ASCENT Plus network, you can see um, how to access this. Here, I'm going to finish my talk by thanking the gallium nitride team who all are working on this and to make this technology happen. And of course, thank you everyone for listening to me.
Thanks very much, Urmimala. I think that was quite interesting. And as you just mentioned, if you have any queries about it or how to access the ASCENT Plus offerings, just contact the ASCESS team through the website, and we'll be in touch with you as soon as possible and try to help you with your requirements and your needs. I try to just sorry, I'll try again. Sorry, guys. So before we go into the questions and answer sessions, what I wanted to do is just a quick announcement. There'll be another one of these ASCENT Plus webinars in a month's time. So on Thursday, May 27th, we'll have a presentation covering again another one of the ASCENT Plus offerings. This time is on 2D materials. It's worked on at Tyndall National Institute in Ireland. So before we go to the live question, we have received a couple of questions on with the registrations. So I think one was quite long. I think you have probably covered most of these items in your presentation, Urmimala. So if you want to have a quick look at this, it's a very long question we got on email, and if you have any further clarifications for what you already presented.
I can go through one by one questions.
Yeah, please. Yeah.
Okay. So why does a GaN device feel a high electric field at the drain side edge? Yeah. Okay. So when there is a high voltage on the drain side, generally, then the gate to drain starts to deplete. And because of the high densities of polarization charges present there, with the slow increase of the drain voltage, the 2-DEG also slowly depletes, and that induces a high electric field, especially near the metal edges. And that is the reason you see mostly the electric field at the drain side gate edge. And the next question is, what is the maximum breakdown voltage achieved in the GaN-HEMT market worldwide? So yeah, if you say what is going on in research, then I would say 1200 volt. So we are also working towards that, and in general, gallium nitride technology is working towards 1200 volt, and in market till today is 650 volt. I think so. Yeah, I think 650 volt, but you can also get one 900 volt from transform. But again, that's a different technology. So that's not like an enhancement mode. So that's a cascode technology actually. In that one, you have one in E-mode HEMT cascaded with CMOS. So these kind of things. But I would say like 650 volt, let's say, for yeah, in market you can buy. What are the major reasons for the breakdown of GaN-HEMT devices? So mainly that's due to layout. That really depends on the gate to drain distance. Let's say for a lateral HEMT, the gate to drain distance matters, like how high breakdown you want. And if the gate to drain distance is too small, then the very high electric field will build up in that region, and that can have a dielectric breakdown. But if the so that is I think the more often phenomena you can have. And if the LGD is large, large enough, then you might see the buffer stack breakdown. But that is unusual because most of the cases you have enough margin. Like if you want to have a 600-volt device, then you will have enough margin for the buffer, like up to 1000 volt or so. So buffer breakdown is unusual, but can happen. Why is the breakdown voltage? So then the fourth question: why is the breakdown voltage analysis done at the off state of GaN-HEMT device? Why not at the on state? Well, it's not only for GaN-HEMT device. For any kind of FET power device, um, breakdown voltage analysis is always done at off state because that's how you want in the application. So a power device is used normally as a switch. So it means when the switch turn off, you want to see that how high voltage it can withstand. And therefore it makes sense that we need to test it in the off state because that is the thing at the end you will use. Why not at the on state? Because in on state, if you do the breakdown voltage analysis, that will be limited by the power dissipation. So you will end up with the safe operating area analysis if you do in the on state. It's not it's mainly coming how you want to use it from the application. We know that the algan. So the fifth question is: we know that algan is the alloy of GaN while increasing the aluminium. So well, it's actually not my field of expertise, but
Yeah,
yeah, I can tell you like
yeah,
aluminium.
that's physics.
Yeah, so aluminium nitride has higher band gap than gallium nitride. So aluminium nitride has, I think, 6.2 EV, and for gallium nitride is 3.4 EV. So by increasing the aluminium, you can actually engineer the higher band gap. And yeah, so that is the main reason. And also another thing is aluminum nitride and gallium nitride actually look alike. And by increasing the aluminum percentage, you will increase. So it's like aluminum takes more and more place in the gallium. So it will have a denser, more condensed lattice. And that is also go hand in hand for a higher breakdown. That's how I can say this. And what is the maximum allowable density of surface donor traps? Okay, so for so the interface of the passivation layer, for the unpassivated, non-passivated layer, let's say, for if it is non-passivated, then the donor traps can be extremely high, and that can go up to 10 to the power 15 per centimeter square. And that is the reason that the passivation is needed. The passivation layer is intended to reduce the amount by several orders. And for the good one, I think we ended up in 10 to the power 10 or 10 to the power 11 per centimeter square. The algan barrier surface, as I said, for the non-passivation, it can go up to 10 to the power 15. The GaN buffer layer, it depends on many things. I don't think that it is easy to say absolute number because it depends mainly on the AP layer, the how you grow it, the quality of AP, and etc. So the kindly relate belly gas figure of merit. Yeah, so that is I kind of say in the at the beginning that I have shown in the graph, right, that how the breakdown voltage is high in case of the gallium nitride device. Yeah, I do not have the graph here. Sorry. Yeah, please.
Yeah, thanks. I think we can go. We have a couple of other questions that were sent online, but I think we could go to any. Is there anyone has a live question? Could you please turn on your microphone and ask, please?
Hello, can I ask a question?
Yeah, sure, yeah.
Thank you very much, Dr. Chatterjee. This is Karim Shirkawi from Tyndall.
Hello.
Just regarding the gate ringing that you described at the start of your presentation, Is it something particular to GaN technology, or can you see it on, say, for example, silicon carbide devices?
So you can see in any device, to be honest. But why I emphasize is because it is particularly a problem in gallium nitride technology, because gallium nitride is a high mobility device, and you will often see the gate capacitance value is, so the QG, the total gate capacitance is lower compared to the other FET, because so this is because the technology specific, it comes from, it inherits property. And that is a reason that gallium nitride is a technology seen which will help to have a high frequency operation. And therefore that CGS value is low, and that is gives a high DVDT. And that charges the small CGS very fast. And that is gives the false turn on, ringing, and everything. So indeed, it is a particular for this technology problem. And when you are trying to design the circuit, you will see that if you do not take care of it, really, this ringing can also easily translate to the output side also.
Very good. And is there any other questions from the audience? Don't forget to turn your microphone on if you want to ask the question.
I would have a question if this is okay.
Oh, hi, Mike. Yeah, sure, yeah.
Hi, thank you. I'm Mike from Leibniz University in Hanover in Germany. So you had on slide 26 the demonstration of the 48 to 1 volt converter.
Yeah.
Do you have efficiency numbers? So what's the efficiency of this conversion that you can achieve?
No, I do not have. So it's really a proof of concept test up to now. But we have the efficiency we have done not for this 48 to 1 volt converter, but for the other converter what I have shown in the prototype level. There we have seen for half bridge switch, we can go for the hard switching, we can go up to 97% efficiency.
Okay, thank you.
Yeah, for the boost converter, yes.
Very good. Very good. We have another couple of questions that also came online. So would you mind answering these ones, please?
Yeah. So this one, like, when will there be a substrate isolation for 650 volt technology? So it is there. It is there, and it is there with us. I got these questions actually before today's presentation. So I have a slide to show.
Oh, very good. Yeah, I'll stop sharing.
Yeah. Okay, now I will share it again. Yes. Yes. So we have GaN-IC in two platforms actually, in 200 volt and 650 volt. We have also used the trench lateral isolation. So we have for 650 volt on SOI wafer and the QST wafer both. And we did like the same trench isolation, and you can see at 25 and 150 degrees centigrade, yeah, it's like even much higher than 650 volt actually. For nominal temperature, it goes even more than 1000, so it's 1200 volt or something. And at 150 is also around 1000 volt. So we have used the same trench isolation, what I have shown in the presentation, like deep trench isolation with the buried oxide and an SOI substrate in 650 volt. Is that answer? Yeah.
Yeah, thanks. Is there any other questions? I think then we can leave it. If you can think of anything or so on, please send me an email. You have my email from the registration, And I'll pass it to Urmimala and we'll try to respond to you as soon as possible.